Hey y'all, this is the notes guide for the Algebra 2 Honors Final. We're going to start with Chapter 1 here. So Chapter 1 was on equations and graphing. One of the first things we learned were the distance formula and the midpoint formula. For the distance formula, that is going to be distance equals the square root of y2 minus y1 squared plus x2 minus x1 squared. Okay, for midpoint, that is going to be x1 plus x2 over 2, comma, y1 plus y2 over 2. Okay? Let's go ahead and do that. So over on the left, y2 minus y1. So your x1 and x2, so your x1, you want that to be sort of the first point, and your x2 to be the second point is in like the greater point, and then y1 is just associated with x1, and y2 is associated with x2. So we'll just plug in. So d here will equal the square root of 6 squared plus 9 squared. Sorry, 9. Just 9. So that's 36 and 9 is 45. So distance is root 45. Over here, we have the midpoint, so x1 plus x2 would be negative 1 over 2, comma, 4, that's 5 plus negative 1, that's 4, so 4 over 2 is just 2. Okay? Alright, moving on, find the equation that goes to the lines to the points. Okay, so this is where you need point slope form. You can do it with slope intercept. The point slope, I think, is a lot easier. This is y minus y1 equals mx minus x1. You see this all the time in calculus. Y1 and x1 are just either of these 2 points. It doesn't matter which one is which. You can use 1, 5 or negative 2, negative 1. And the m is the slope. So remember that slope is going to be rise over run, y2 minus y1 over x2 minus x1. So when we plug those in, we're going to get 6 over 3, which is 2. And so I can just choose either of those 2 points to plug in for y1. I'll go ahead and just choose x1 and y1 here. So it'll be y plus 1 equals 2 x plus 2. Okay? Find the equation of the line that passes through 1, 1 and is perpendicular to the line at C. So if it's perpendicular, then the slope needs to be the opposite reciprocal, so negative 1 over m. So in that case, if my original slope was 2, then my perpendicular slope would be negative 1/2. So, and it has to go through 1, 1. So it's the same idea. You're going to use that point slope formula. We're going to get y minus 1 equals, but this time, negative 1/2 x minus 1. Find the equation of a circle centered at 2, negative 3 with radius 6. Sketch the graph. So equation of a circle is x minus h quantity squared plus y minus k quantity squared equals radius squared. This is really familiar with ellipses. It's just like a simpler version, right? We're adding 2 squared values, there's no division, and then the center, right? This is the center hk here, and then your radius is 6. Right, this is your r. So you're just plugging in. So we're going to have x minus 2 squared plus y plus 3 squared equals 36. Okay? All right, continuing on. All right, we got some quadratics. So we have different ways to solve quadratics. Factoring, complete the square and quadratic formula. So factoring, if your a right here is not 1, you can use different methods. You can do the sort of guess and check box method, which some of you may have learned, where you put 2x squared here and negative 3 here, and you're basically just, you know this has got to be 2x, you know this has to be x, And you know this has to be like some combination of 1 and -3, and you're just testing them until you get -5 here. So, okay, well, I could put a -3 here, which would give me a -x, and you could put a 1 here, but that wouldn't add up. So the -3 has to go here, and the +1 has to go here. That'll give me x, and then -6x. And these two add up to -5x. That's how I know I've got it right. So we have 2x plus 1 and x minus 3. The other way you can do it is the ACB method, where you do AC on top, so -6 on top, and then -5 on bottom, and then two numbers that multiply -6 add to -5 are -6 and 1, and then you split up the function to be 2x squared minus 6x plus x minus 3, and then you factor each, you kind of split this and factor each side, so you end up with 2x x minus 3, and then plus x minus 3, so your factors are also 2x plus 1 and x minus 3. So either of these two ways work. Complete the square, right? You set it equals 0, 2x squared minus 5x minus 3 equals 0. You move the constant over, 2x squared minus 5x equals 3. You factor out a on the left side, so we're going to have 2x squared minus 5 over 2x equals 3. And you're going to add b over 2 squared to both sides. And that in this case would be 5 over 4 squared. So, no, before we do that, let's divide this by 2. You could add b over 2 squared here, but let's just divide both sides by 2 first. We get x squared minus 5 over 2x equals 3 halves. Then we'll add b over 2 squared to both sides, and that'll get us x squared minus 5 over 2x plus 25 over 16 equals 3 halves plus 25 over 16. When we combine these two together, you're going to get 49 over 16. And then when I rewrite this as a perfect square, I'm going to get x minus 5 over 4 squared. And then from here, you just solve for x. Okay, so you square root both sides. You end up with x minus 5 over 4 equals plus minus 7 over 4. And then from here, you just get x alone. Okay, so your final answers should be x equals 3 and x equals -1/2. Okay, quadratic formula, we know this, right? X equals negative b plus or minus the square root of b squared minus 4ac, always, or 2a, always good to know. And you just plug in, right? Your a is 2, b is -5, and c is -3. We just plug in here, okay? All right, finding y-intercept from vertex. I know I kind of ran out of space here, so y-intercept is easy. Y-intercept is just f of 0, right? This will always be the y-intercept, just plug in 0. And then the vertex is, there's different ways you can do it depending on what form you have, but negative b over 2a, comma, f of negative b over 2a would work in this situation because you're given ax squared plus bx plus c. If it was given to you in factored form, right, you could take the midpoint of the zeros, and that would be your x value. It's like it's p plus q over 2, and then f of p plus q over 2. This is just the midpoint of your zeros, and then the output of the midpoint of your zeros. Same thing. Okay. In this case, you have just be prepared to mark the zeros, the y-intercept, and the vertex. Okay. Just label the above features. Okay. Complex numbers. Let's mix this up a little bit. Let's make this a plus. Let's make this a multiplication. When you're adding complex numbers, you just combine like terms. So 3 and 4 is 7. -4 and 2 is -2. So it's just 7 minus 2i. Here you just subtract as normal. -1 and 6, so it's negative 1 minus 6i. And then here, when you multiply, I think box method is a good place to go. We're going to have 3 minus 4i and 3 plus 4i, and we'll multiply in the middle. So 9 minus 12i here, 12i here, and then we're going to have a negative 16i squared. But because I squared is just negative 1, this just becomes 16. And these two will cancel. So 16 and 9, this is just 25. Okay? I to the 33rd. So remember that I to the first is I squared is negative 1, I to the third is negative I, and I to the fourth is 1. So the way you solve I to like a high power is you take that power and you divide it by 4, and you take the remainder. So, okay, what's the biggest number that goes into 33 4 times? Well, that's 8. What's the remainder? The remainder is 1. So that would mean, because the remainder is 1, that the answer is I to the 1, or I. Okay? That's your answer. All right, inequalities and absolute values solved by graphing on a number line. So here, for the first one, we just got to get x alone. So subtract 2x on this side, subtract 2 on that side, you're going to have negative 5 is greater than 5. Sorry, negative 5 is greater than 2x, my bad. And then negative 5 halves is greater than x. So on the number line, it would be, you'd have an open hole at negative 5 halves. We're saying x is less than it, so it's just going to go down. Okay? This one is like an and statement, so it needs to be both of these things. So we can rewrite this as 2. 4 is less than x minus 5, and x minus 5 is less than or equal to 9. So we'll have 9 is less than x. Sorry, x is greater than 9. Same thing. And then x is less than or equal to 14. So on a number line, you'd have a filled in at 14, you'd have an open at 9, and you would just connect the two. For absolute value, you have to account for the inside of the absolute value being negative. So when it's an equality, you can say, okay, x minus 4 could equal 3, but it could also equal negative 3. And we solve from there. So we can have x equals 7 or x equals 1. Either of those would work here. When it's an inequality with an absolute value, it could, same thing, it could just be greater than 4, or it could be less than negative 4. I know that's kind of confusing, like why are we switching the signs? I think like, the way I think of it is like, it's like a magnitude, right? The magnitude of the number needs to be 4 or larger, or negative 4 or smaller. Like, that's how I think of it anyway. So from here, x is greater than 1, and from here, x is less than negative 7. And this is an or right here. So greater than 1 and less than negative 7. Okay? Good. All right. Okay, chapter 2, functions. So these are the parent functions. 2 are not functions. Can we find them? So let's make sure we're familiar with these. Okay. Y equals x. Should be pretty straightforward. Just a line with slope 1 going to the origin. Y is negative x. See, you can do these without me doing it, right? Line through the origin, slope of negative 1. Y equals c. That is just a horizontal line. X equals c. That's just a vertical line. Okay. X squared. That's our quadratic going through 0, 0, going up, right? X cubed, cubic function. So that is also going to the origin. We do go, it's an odd function, we do go positive infinity on the right, negative infinity on the left, because we're cubing. Okay, root x. Root x does not include any negative values, and it kind of looks like half of a quadratic on its side. I mean, that's what it does look like, right? Cube root of x, similar to how root x is kind of transformation of x squared. This also looks similar to x cubed, to rotated 90 degrees and then reflected. Okay. 1 over x, what does 1 over x look like? So as we get closer and closer to infinity, right, it's going to get larger and larger, and as we go away, as we go closer to 0, it gets larger and larger. As we go away from 0, it gets smaller and smaller. And when we're negative, right, we go similarly go down to negative infinity, and as we get larger and larger, closer and closer to 0, but from the negative side. Okay, absolute value of x, right, similar to x, but it's a V shape because it always has to be positive. E to the x. Okay, so plug in 0, you get 1. Okay, e to the 0 is 1, so we're here, and we will get exponentially larger as we move to the right, and we will approach 0 as we move to the left. Okay? ln shares similarities with the e to the x. The difference is it's e to what power is x. E to what power is x. So when x is 1, this is an easy point to get. When x is 1, this must be 0. E must go to the power of 0 to equal 1. So we have 0, 1 on e to the x, but we have 1, 0 on ln x. And then from there, as we decrease, we have smaller and smaller numbers. As we increase, we need larger powers. And we cannot have a negative negative input here. Okay. All right, sine x. Okay, just remember that sine, we're on the unit circle, right? And we think about, we start over here at 0, and so what's the x value, what's the y value, sorry, at 0? Well, it's 0, so we start at 0, and then we increase to 1, and then we decrease to negative 1, and we're back to 0, right? And this whole thing happens over 2 pi. And then it repeats the reverse way, right? So, and that would be negative 2 pi, okay? Cosine, very similar to sine, except that it starts at, not at 0, so it's at 1, and it decreases to 0, and then to negative 1, and then back to 0, then back to 1. So I kind of put along, and that's Alexa 2 pi. Okay, and then you're looking at the x values here. Tan x is the ratio. Remember, tan is sine over cosine. And so you have these vertical asymptotes whenever cosine is 0. So where is cosine 0? Well, cosine 0 at pi over 2, right? And cosine's also 0 at 3 pi over 2. Okay. So you can go ahead and kind of sketch those vertical asymptotes. And then when sine is 0, it just equals 0. So when does sine equal 0? Sine equals 0 at 0 and at pi. And then from there, as we get closer to pi over 2, because both values are going to be positive, but cosine is getting smaller, we're going to go up to infinity. But after pi over 2, now cosine's negative, but very, very small, so we're going to group it down here, and then it kind of follows that same pattern. Okay? And then that mirrors itself here. Okay? X squared plus y squared is r squared. We just did this in the previous page. This is the area of the circle. Sorry, not the area, the equation of the circle. So, this distance here, that's your r, and we're centered around the origin. Okay? Transforming functions. Okay. So we have different values that can transform the function, right? The d, this is your vertical shift. This c is your horizontal shift. This b is the horizontal stretch. And then the a is the vertical stretch. So let's look at these functions, what's going on. So this would be, let's just list what's going on. We have vertical shift up 2. We have horizontal shift right 4. So this is a quadratic going up 2, right 4. That. Okay. This one, we have a vertical shift down 3. We have a horizontal shift right 4. And then we have a vertical stretch by factor 2. So how does this look? This is an absolute value function, but we're going to write 4 down 3, and it would be twice as steep, right, as a regular absolute value function. 5 sine 2x, so this is a vertical stretch of 5 and a horizontal shrink of factor 2. So let me go back up to this for a second just to clarify. It's a horizontal stretch if b is less than 1, but it's a shrink if b is greater than 1. And then the same thing with like the horizontal shift. If c is positive, it's going to go to the, it's kind of confusing because it's like there's already a negative sign in here. See that? So if c is a positive, using this form, c is positive, it's going to go to the right, and if c is negative, it's going to go to the left. Okay? All right. Find average rate of change for a above from 3 to 6. So average rate of change, or AROC. This is f of b minus f of a over b minus a. So for a, this one up here, it would be, this is rewritten as, this is your a because it's lower, and this is your b because it's higher. F of 6 minus f of 3 over 6 minus 3 would be, so we'll plug in a 6, we'll get 6. We'll plug in a 3, we'll get 3 over 3, so it's just 3 over 3 or 1. Okay. Function notation and combining graphs. So this is pretty straightforward. These first two here, you're just plugging in 2 for x. So f of 2, right? That's just 2 times 2 plus 3. That's just 7. G of negative 2 plus h of 2. You're just doing two different functions at once and adding them together. So 1 over negative 2 plus 5, right? So that's 4.5. F of g of 2. This is called composite function. This is where you plug 2 into g and then plug that output into f. So if we plug 2 into g, that's 1/2. So we would plug 1/2 into, right, see that up here? 1 over 2, that's g of 2 is 1 over 2, and we're going to plug that into f. So it would be 2 times 1/2 plus 3, or that's 4, and that's because this is g of 2. Okay. H of g of f of -2, same idea. You're just doing 3 at once, so f of -2, so over there is -1. And then we're going to plug the -1 into g, so then g of -1 is also -1. And then we'll do h of -1, which is 2. That's your answer. F of x plus 1. So f of h of x plus 1. So this means plug in x plus 1 into h. So h of x is x squared plus 1. You see that? So if we do h of x plus 1, that means it will become x plus 1 squared plus 1. So that's x squared plus 2x plus 1 plus 1. So that's x squared plus 2x plus 2. And then we're going to do f of that. So f of x squared plus 2x plus 2 just means plug this in for the x value of x. So that would be 2x squared plus 2x plus 2 plus 3. Okay.
What is this?
So inverse functions graphically and analytically. Let's start with analytical. So the steps are 1, switch x and y, and then 2, solve for y. So pretty straightforward here. We're going to have x equals 2y cubed minus 3, so x plus 3 equals 2y cubed. So that's x plus 3 over 2 equals y cubed, and then we're going to cube root. We'll get y equals the cube root of x plus 3 over 2. Okay? So that's it analytically. You just switch x and y and solve for y. Graphically, what happens is, let's graph the function, and I'll show you how to find it. Okay, so continuing on, if we were to graph these, you would get, if we graphed 2x cubed minus 3, it would be sort of down here, 1, 2, 3, and it would sort of create this, this cubic function here. And if we were to sketch the inverse, it's going to be reflected over x equals 1. So you can kind of even count boxes up and down, left and right, to mirror it over, but you're just reflecting it over this. So when you do that, you get this cube root function, which looks like this. Okay, so it's reflected over x equals 1. That's the main takeaway for graphing. Reflect over, so not x equals 1, y equals x. Okay. Prove that two functions are inverses. So you can prove that they're inverses if you take the composition of each other, and it equals x. So in this case, if we did f of g of x, it would be 2 times x plus 4 over 2 minus 4. That would be x plus 4 minus 4, which is just x. So by composing them, you get x. That makes them inverses.